We now want to talk about gravity as applied to orbits. We're dealing with the course involving the solar system. We've talked about how the planets orbit the sun in ellipses, and we want to talk about orbits around the Earth just a little bit as well. So a little bit more with gravity. Do you think heavier objects fall to the Earth faster than lighter objects? Do you think an object that has more mass will fall to the Earth faster than an object that has a smaller amount of mass? Well, we know that the force acting on the object is greater if the mass is greater. Let's just take mass of the Earth to be fixed, and let's drop different objects a couple meters off the Earth and drop them and observe them moving. There's going to be a force, a gravitational force, that's pulling the object down. It has a weight that's downward. So if we have mass 1, we get a certain force. What if I have 3 times mass 1? If the mass is 3 times greater, will the force be 3 times greater? If we leave g the same, it is a constant. If we leave the mass of the Earth the same, there's only one Earth that we're dropping these objects towards, and we leave the distance the same down to the center of the Earth, we drop all the objects from just 2 meters above the floor. So g, m, and r are held constant. We're just varying mass 1. We get a certain amount of force with mass 1. If we take an object that has 3 times the value of mass 1 for its mass, the force will be 3 times greater. So will it fall faster? Will it fall faster? Well, there's something else to consider. These objects, as they're being accelerated, have inertia. And we talked that an object that has more mass has more inertia. It's harder to accelerate. So look at this. We've got more force. The object does way more if it has 3 times the mass, but it has 3 times more inertia. And the two effects do cancel out. All objects accelerate at the same rate as they fall. This is ignoring air resistance. So you have to choose objects that are relatively dense, that air resistance is not important. But it is true that if you ignore air resistance, all objects fall at the same rate towards the surface of the Earth. You might look for a YouTube video, Galileo's experiment on the moon. Galileo's experiment on the moon. And this experiment was done by astronauts with a feather and a hammer. And on the moon, where there's no atmosphere, they hit the moon's surface at the same time. So let's test this on the Earth. Well, if you're Galileo and you have access to climb up the Leaning Tower of Pisa, then you could go ahead and do that. And I'll let you go to this link here. That's Galileo's experiment on the moon, with the misspelling of Galileo. But suppose we'd climb up the Leaning Tower of Pisa. I took this photograph, but I did not climb the tower. Then you lean over the railing carefully, and you drop 2 dense objects, but one is more massive than the other. And your assistant at the ground, standing off to the side, observes them hit at the same time. So confirmation that objects with different mass do have the same acceleration. This has been very well tested. It is true. So mass of the Earth. How can we find the value of the mass of the Earth? We want to know how many kilograms are in the Earth. How could we succeed at doing that? Well, we can measure gravitational force. We can measure the weight of objects. The constant g has been measured in the laboratory. Suppose we take a known mass and we can survey and find the radius of the Earth. So if we know these 4 quantities, F, G, M1, and R, if mass of the Earth is only unknown, yes, we can calculate it. And this was done around 1800. The value of g was measured in the late 1700s, and people realized then they could calculate the mass of the Earth. Is there any other way that the mass of the Earth could be determined? The answer is yes. It has, of course, the Earth has a gravitational effect that goes out into space, and the Earth will cause small asteroids that are passing by the Earth to be changed in their orbit, be deflected. The Earth's mass will cause that to happen, and that's another way you can get the mass of the Earth. So centripetal force, let's move on towards orbits. When we have an object that's moving in a circle, and for my class, if I remember, I'll put a rubber stopper on a string and swing it around my head. We need a centripetal force. We need a force towards the center to cause an orbit here. And for the case of the rubber stopper on the string, the tension in the string will supply that force. The speed of this object will be constant. The velocity is changing because the direction is changing, but the speed will be constant. And the force that will cause this to occur can be calculated with mass of the object that's in motion, the square of the speed, and divide by the radius of the circle. We are not going to do that calculation, but this is how you could do it and find the strength of the centripetal force. Notice that if the speed goes up, if I double the speed, it's going to take 4 times more force because the speed is squared. This is v squared, this notation. If I triple the speed, it's going to take 9 times more force. If I have a smaller circle at a given speed, that's going to take more force to turn this more quickly, causes a higher value of acceleration. So this relates a little bit to driving a car around a curve. You'll see a speed limit posted. There's a certain amount of frictional force that's available. That frictional force is directed towards the center of the curve and keeps your car going around the curve. If the road is icy and you don't have as much friction, you don't have as much centripetal force towards the center of the curve, then you can go off the curve. What would happen if we would cut the string or release the string? Then the object moves in a straight line. That's Newton's first law. If we get rid of this force and in the horizontal direction now have a net force of 0, the object goes off in a straight line. So that's kind of the basics of orbits. We need a centripetal force, a rubber stopper on a string. The string supplies that force. An object moving around the Earth's gravity supplies that force. So orbits, and get a cannon here, and we shoot a cannonball out of the cannon with a certain speed. And if we do that, if we shoot faster and faster, we can get the cannonball theoretically to orbit the Earth. That's tough with the atmosphere. So we need to get above the atmosphere, and we have in the late 1950s, a great race, space race, occurred between the United States and the Soviet Union. And here's an example of a rocket launch, and the press is there to record it with no protective bunker, not too wise, but there they are. The Soviet Union was the first to successfully orbit a satellite around the Earth. So October 4th, 1957, had radio antennas on it and sent a radio signal back to the Earth that everyone could hear and confirm this object was in orbit. The United States followed in January of 1958, putting Explorer 1 into orbit and had scientific equipment on it that reported back conditions in space. A great success, political sort of parity with the Soviet Union was achieved. And kind of interesting here, the person on the right, Wernher von Braun, the leader of the United States space program, a German rocket scientist from World War II. In the center, Dr. James Van Allen, and just a personal note, he taught general astronomy at the University of Iowa for many years, and I worked as his student assistant for 4 years, teaching labs for the general astronomy course. So University of Iowa was crucial in putting together the equipment, the scientific equipment that made measurements and came up to deduce the Van Allen radiation belts. We'll study those more later. A little bit more currently, Space Shuttle has not been flying for several years now, but larger rockets, more complicated payload, and Space Shuttle being launched here in this frame. To get into orbit, roughly you need to be traveling 17,500 miles per hour in the forward direction, so that as the Earth tries to pull you towards it, and it does accelerate you towards the Earth, you're moving forward, and consequently you don't hit the Earth. You're moving forward, the Earth is curving away, the Earth is a sphere, not flat, so we can orbit around that sphere if we achieve this orbit velocity. and low Earth orbit International Space Station that the space shuttle is docked to in this photograph, about 250 miles altitude, the distance above the surface of the Earth, only 250 miles. Our atmosphere is relatively thin. Our atmosphere, 35 to 50 miles thick, depending on where you want to measure thickness. In Skylab, let's talk about this apparent weightlessness effect. So is this astronaut holding the other astronaut just with one finger? And no, there's no contact force here. Both the Skylab is in orbit around the Earth. The astronaut, this astronaut's in orbit, this astronaut's in orbit, and they're all orbiting the Earth more or less independently. There's no contact force required between the objects. They're all in orbit. They're all really in free fall towards the Earth, but again, moving forward so they don't hit the Earth. And they're apparently weightless. They still have a weight. There is gravitational force pulling them towards the surface of the Earth, but apparently they're weightless. More modern, in the International Space Station, there's more room, so they can have more astronauts. And these astronauts are not flying like superheroes. They're just made themselves no longer in contact with other astronauts or the walls of the inside of the space station here. And they're all apparently weightless. Not truly weightless, but apparently weightless. Interest on the bottom corner here for viewers who are from Nebraska, Clay Anderson from Ashland, Nebraska, in between Lincoln and Omaha. And another photo with Clay has made very good contributions to our space program. In space, the body gets used to up, down, left, and right orientation. There's no sense of being pulled here and being a sensing of upside down. Again, apparently weightless. And now geosynchronous satellites. Geosynchronous satellites. The Earth here is spinning. In one day, or complete one revolution, it turns out there's a distance away from the Earth, and my memory is a little foggy here. I think it's about 22,000 miles, where the time for one orbit is also 24 hours. In that situation, suppose we have a satellite antenna on the roof of our house pointed towards the dish TV satellite, and that antenna does not need to be adjusted during the day. If the dish TV satellite is in a geosynchronous orbit, the orbit takes 24 hours, the Earth spins once in 24 hours, and we do not have to try to track the satellite across the sky. The motion of the Earth automatically moves the dish to keep in line with the satellite. A very important communication belt here, the geosynchronous satellites, setting up communication satellites from many different countries are in position here at the Earth's, above the Earth's equator, but they take 24 hours to complete one orbit. Thus, they always are in the same spot in the sky, and your dish can just be lined up one time, and you're good for several years, unless a tree branch hits it. There is a problem with debris in space. The United States government tracks, and other governments as well, with radar, tracks small pieces of material that are in orbit around the Earth. There have been some satellites explode in space and various debris created. So there's really a tremendous problem building up with too much debris. And this debris is hazardous. It's moving at thousands of miles per hour. And some of these orbits crisscross each other and can produce collisions. So about 19,000 objects with a size a little over 4 inches, 10 centimeters. And we've got the Earth here and then all this space debris. And there may not be quite 19,000 dots on here, but there are many objects being tracked to try to keep our astronauts safe, and from their orbit intersecting the orbit of some of this space debris. So we have gravity that causes these orbits. Gravity supplies the centripetal force, and keeps our objects accelerating towards the Earth, but they're moving forward so they don't hit the Earth. We achieve orbit at about 17,500 miles an hour. Question for you, what if we went faster? What if we went faster than 17,500 miles an hour? Well, then the orbit would become more elliptical, and if we go even faster, about 40% faster than the velocity for a circular orbit, if we go 40% faster, that's escape velocity, and we would move out into the solar system. We would no longer orbit the Earth. Then, if you go even faster, you can escape from the sun. And there are 4 Earth-launched satellites that are leaving our solar system. They have enough speed to escape the pull of the sun's gravity. So keep reading about that. We'll talk more about that later. Here is a graphic that shows the moon and the Earth. And it turns out there's a common center for these objects that orbits the sun. That's the black line here. And here, they're not to scale, much exaggerated, but the Earth moves back and forth, inside and outside, compared to where this center of mass line goes. How would we draw the moon's orbit on here? If this represents the wiggling of the Earth back and forth, as the moon is on one side of the Earth or the other, well, the moon would have a much larger wiggling back and forth. The moon is 81 times smaller than the Earth. So just as, and this you can see not to scale, but the moon is on the opposite side of this center of mass line as that center of mass moves around the sun, but the Earth on one side and the moon on the other side of that center of mass line. So let's see if I can go a little further here. We are getting near the end, and guess what? We're at the end. So just kind of interesting here. The Earth does not move in a smooth ellipse around the sun. Because of the presence of the moon, the Earth wiggles back and forth a little bit. So that's where we're going to stop our conversation, and I hope you keep reading and asking questions.